Yeah, I'm going to talk about drainage water management and what the potential impacts are for addressing water quality issues in the state. So if we, driving across the landscape, we see a lot of this. There's a lot of tile going in. Somebody showed a figure earlier, I think it was Greg, based on a survey here, and I saw some counties that were down at 50%, and that's hard for me to believe. Just what I see across the landscape and knowing the soils that we have here, that drainage is, my guess, is probably at the minimum 80–85%. So anyway, we're going to talk about potential for drainage water management. So when we look at the landscape, we see a lot of this. I mean, if you look at, there's an old aerial view. This was back in the 50s. We see tile drainage. This is 50-foot spacings. This is one of the engineering drawings. So what's happening today is this. We're going in and splitting tile. How narrow is narrow enough? When we look at this picture here, literally, and I talked to a producer the other day, they were going through the field. The tractor tires, they were planted in themselves, were on top of the ridges. I mean, we're talking 12 feet. Do we need tile at 12 feet? I understand there's some reasons for putting tile in. You put the economics back. See, I don't know how to use it, Greg. So you're putting the economics back in the field, and there's probably some benefit to it simply from you see a benefit. Why is that? We can get into a whole nother discussion about that. My feeling on that is we've destroyed our soil structure. Our equipment's getting bigger. Our windows of opportunity are getting smaller. So we're going out there with this larger equipment. The soil's just a little wet, so we're compacting and compacting and compacting. So we don't see the benefits of that tile drainage at that 50 and 60-foot spacing. So we're going in and we're splitting that. And when we do that, we have a water quality potential issue with that. We're transporting more. So when do we need tile drainage? And this is just an annual graph of looking at the precipitation, the potential evapotranspiration, and this is, like I said, this is a 5-year period. So when do we need tile drainage? We need tile drainage when we're out there ready to plant, needing to plant, and we need it when we harvest. Do we need tile drainage at other times of the year, at least as severely? Yes, last year we needed tile drainage a lot. There are times that we do, but in general, those are the times that we need tile drainage. And so the other times of the year, we're proposing that we can use a practice called drainage water management to potentially hold some water back. So artificially raising that outlet elevation. And this is a graphic that Norm Fawsey provided. And then we're all familiar with this. So on the bottom is sort of what that looks like from a tile drainage standpoint in terms of we put these structures in the field. And then, here we are in the non-growing season. So after harvest, the fallow period, we can actually artificially raise that outlet elevation to about 12 to 16 inches from the surface. We don't necessarily need to let all that water go down the drain. We open those boards, we release that water, we get if there was water table behind it, we release it, we get it back down to the tile depth, and we can plant. Okay, after planting, we do all our field operations, do our side dressing. You know what, we can raise that outlet elevation again up to probably 16 inches or so, and there's a lot of benefits. Someone mentioned earlier this morning that farmers are doing this because they want to take advantage of that water. Well, that's only potential. Okay, we've got to understand drainage water management is not an agronomic practice. It's a water quality practice. We need to understand that. So if there's water there, we might see some potential benefit to yield. But understand it's a water quality practice. So we maintain that. During the growing season, we bring that up to about 16 inches, and we can let that go through the growing season, and then we can reduce or raise those boards again, or lower them, whichever way you want to look at that. But to let go of that water if there's any there, and then we can harvest, and then we start the process again. So this is the idea of managing these when we start looking at these structures. So let's look at the existing structures that are out there right now. Somebody said this morning, and I forgot who, Terry Mesher, I think, talked about 1,200. The last number I got, which was a year, 18 months old, ODA, ODNR, there were 902 structures in. NRCS has put in approximately 600 structures. So we got somewhere around 35 to 40,000 acres. These structures handle somewhere in that 15 to 20 acres apiece. So about 40,000 acres that are under drainage water management right now. So the question is, you know, we put these out there based on, there was a study, Norm Falsey did a study at Hoytville at the research station there on 12 plots, very small plots, and they showed a big benefit in terms of reducing nitrogen. They can store some water back. The question is, do they have an impact on phosphorus? And if we look at the literature, and we're going to talk a little bit about the literature, there is some suggestions that there's some benefit. There are roughly, with respect to phosphorus, there's 10 site years of data is all that we can locate in the literature. That study one of those studies comes out of Minnesota, one out of Illinois, one out of Sweden, and the other one is here in Ohio right outside of Columbus. So a very sparse set of data that was used to say, yes, there's potential benefit to phosphorus. So the objective that I'm going to go through today is to quantify the effect of this drainage water management practice on the discharge, the nitrate, and the DRP loss that we see coming from the edge of field. So I'm going to try to get you oriented here of what we did. This is the only graph you're going to see on the methodology. But what I want to talk about is what we use. Our approach is to use a before-after control impact design. And so when we go into a producer with any of our edge of field practices, we've gone in and we said, look, we want you to, we want to collect baseline data. We want to collect data for a couple of 3 years to see if there's a relationship between the treatment field and the control field. And so that's this line here. Okay, that's what we're looking for, is to see if there is a relationship there. Then we implement some type of a change. And then we want to measure that again for a 2 or 3 year period. And we want to see, was there a shift in that line? Did the phase drop? Did we see an impact of this treatment? Remember, the y-axis is the treatment. And so we're looking for that drop in the line, and specifically these means. So this is the mean of the data. Where the mean occurs is this line here. And so once we identify that, we're looking to see what is the difference between that control mean and the treatment mean. And by doing that, then we can have an understanding of what the impact is of that specific practice. So as we go through this data, we've got 2 field sites that we're going to go through. So that's what I'm going to do next, we're going to talk about a little bit about some of this data from the sites. So the first site, this is in Wood County, Ohio. These are 2 roughly 40-acre fields, both the control and the treatment. It's side by side. So it's a Hoytville silty clay. It's 0 to 1%, very flat. The soil test P on this is 58 parts per million in the control and 48 in the treatment. So a little bit above the agronomic level, but not out of whack by any means. This is a corn, soybean, wheat rotation with annual cover crops in general. Now they've been sparse at times. They haven't gotten them planted or haven't gotten good stands. And I put minimal tillage in here. We've tilled twice in the 5-6 year period that we've been there, and again it's been minimal disturbance. This is a vertical till type system. The fertility is starter with corn and wheat crops. And again, as I showed you the graphic earlier, drainage water management, we manage both during the winter and the summer, so all year we manage this, if you want to think about it that way. And that when we did manage it, those boards we were bringing them to 16 inches from the surface. So again, we've got 5 years worth of data here. So water year 14, 15, 16, or I think that's supposed to be 15, 16, 17, and then the treatment is water year 18 and 19. So 3 years of the baseline and 2 years of the treatment. So let's go look at the data. So when we look at this, we've looked at this again from a discharge standpoint, a concentration of nitrate as well as the loading and the dissolved phosphorus concentration and loading. So think about this. This is that, remember, the means, the control mean and the treatment mean. So that's on that graph, okay? What is the difference between those? So red means we actually saw an increase. Green means we saw a decrease. And this has to do with surface runoff. So remember, if we are actually holding water back due to the drainage water management, we would expect to see a little bit of an increase in the surface discharge. And in fact, that's what we see. And again, we use monthly data. So if we look at this that's a monthly basis, so we multiply that by 12, and we can get our annual difference. So on this particular field on the surface, we saw an increase of about 0.6 of an inch of water over the year due to drainage water management. We saw a decrease in the nitrate concentrations and the nitrate loading to the tune of about, and we don't expect to see a lot of nitrate benefit at the surface. That's usually a subsurface thing. But with respect to concentration and phosphorus loading, we saw an increase. So, we hold more water back, see a little bit more coming off the surface. I have these are the percentages on the bottom here of what those look like. And then if we look here, the box indicates that it was significant. So again, keep in mind that we do these statistical tests. And so these are trends, if you want to think about it that way. This is the direction it's trending. But then we do have some that are significant. When we do our statistics, it would say absolutely, we're confident that there's a difference there. So that's where we are with the surface on this particular site. If we look at the tile drainage results from this drainage water management treatment at this site again, we see that we held water back behind the drains to the tune of about 1.2 inches over the year. So we had that much less water going down the system. Again, saw some benefit with respect to nitrogen in terms of the concentration and with the loading. So if we look at it on an annual basis, we saw about 2 pounds per acre less nitrate nitrogen going down the stream, going out of that tile with drainage water management. However, with respect to phosphorus, we actually saw an increase in both the concentration and the loading associated with that. There was a question this morning about redox potential in one of the other talks. And so we have iron in these soils, we get that phosphorus on that iron, we go anaerobic, we can take some of that and strip some of that phosphorus off, and that's what we believe is happening here. Again, when we look at the difference though on a 12-month basis, pretty small, 0.001 pounds per acre increase. Doesn't sound like a whole lot, and it's not. But we'll look at the cumulative effects here in just a minute. Again, the only statistically significant difference was with nitrate concentration, which we saw on a monthly basis go down by about 2 parts per million. So now we're going to move to a different site. And the site's in Crawford County. A little different cut of the field. So you can see the sort of this orange line here is the surface contributing area. The red dashed is the tile. Dashed down here is the tile, and the solid is the surface discharge area. So again, drainage areas are just a little bit different on these, but again, for this process, we're looking for similar responses. They don't have to be exactly the same. We want a relationship is what we're trying to develop. The soils are here. We've got a Pewamo silty clay and a Bennington silt loam. We got a little bit more slope to this field than we did on the other field. Soil tests are in that higher agronomic range, 33 and 40 parts per million. This is a corn-soybean rotation field with its rotational tillage, so tillage before corn planting. The soybeans are no-till. The fertility here, he does variable rate in the fall before corn, and then it's incorporated. So usually with that implement again that he's tilling with. That's a disc chisel primarily at this particular site. Drainage water management, exactly the same as the other one, at around 16 inches. And again, it's water year 15 through 17, so 3 years of data, pre-treatment data, 2 years of post-treatment data. So we look at, again, now we look at the surface runoff from this site, and we actually see a decrease in the surface runoff. Not exactly sure why. We see a decrease, but to the tune of about 1 inch per year. And then we see on this particular site with the surface runoff, we see increases in the nitrate and the dissolved phosphorus concentrations and loadings with that. So again, I guess I should have pointed out too, and I failed to do it on the other graphs if you were wondering, these R-squareds, and that's the most likely reason for this here is the scatter here. These relationships are not as strong as they were in the previous field, so we get more scatter in that data. So there's more uncertainty driving some of that difference. But again, from a statistical standpoint, we did see an increase in the dissolved phosphorus concentration. Again, this is in the surface. If we look at the subsurface on this particular site, we generally see a benefit of drainage water management. Again, discharge, we held about 4 inches per year of water back on this field. We saw a reduction in the concentration of about 5 parts per million of nitrate concentration, and we saw about 3.5 pounds per acre of nitrate nitrogen load that did not leave the site because of that. We did see an increase in dissolved phosphorus again. Again, most likely that reducing condition. We're holding more water back. We're keeping that soil wetter, and it goes aerobic. We're going to potentially get some reduction, and we'll get an increase in that dissolved phosphorus. The reason we don't see a load necessarily increase is because we held more water back. So this is we talk about, if you hear of other people talk about it, you look in the literature, they say, well, the benefit to phosphorus is because we're holding the water back. We're holding more water back. Well, in the first case, we weren't able to hold, we held 1 inch back. So remember, we didn't hold enough back to overcome what that increase in concentration would be. Here, we held enough water back to overcome that. And so we saw a significant benefit to that. And again, from a statistical standpoint, discharge, nitrate concentration, and nitrate load, these were all significant differences associated with that. So now I'm going to try to bring all of this together just from the Maumee Basin, if you will, perspective. So if we look at the total area in the Maumee River watershed that's suitable for drainage water management, we're looking at about 2.5 million acres. And that's ag land with less than 2% slope that are poorly and very poorly drained soils. And so you can see where the distribution of those soils are in those sites. So the potential impact on discharge, if we combine these two, if we look at this study, we saw an increase of about 6 tenths of an inch per year to a decrease of 1 inch per year. Tile drainage, we saw a decrease of about 1.2 to 4.1 inches per year associated with this practice. If we look at what the previous studies say, surface runoff, they showed about a 33% increase, or 1 inch per year increase in surface runoff. Again, we show on one of the sites, we did show about 0.6 of an inch per year. And then tile discharge, they saw a 46% reduction, which was about 5.5 inches per year. And if we look at this plus or minus 10%, sort of where we are there. So in that 4-inch range, we're sort of in the ballpark. So I would say our data is in line with what we especially see on tile drainage. The impact on nitrate loads. Okay, if we look at our study, we saw an increase of about 0.66 pounds per acre, which was about 1.6 million pounds of nitrate that was increased, to a decrease in the surface of about 0.26 pounds per acre, or 650,000 pounds decrease of nitrate nitrogen. In the tile, though, we saw a decrease of about 5 million pounds to about 9 million pounds of nitrate nitrogen by using this practice. Okay. Previous studies, again, they show an increase on the surface, and there was 10 site years of that. Again, our number was just a little bit higher than that, about 0.66 to 0.3. But in the tile drainage, it was very similar. Again, these studies, one in Minnesota, one in Illinois, a lot more nitrogen coming off of those systems. And so we look at 12 pounds per acre. Ours here were 2.1 and 3.5. But again, so benefit to nitrogen. We absolutely see that, and we were able to measure that. With respect to phosphorus, okay, our study showed, again, an increase of about 0.03 to 0.04 pounds per acre per year. So that's about 75 to 100,000 pounds that we're adding of phosphorus if we're using drainage water management. Again, this is based on 2 fields where we measured our data. Tile discharge in the surface actually showed an increase again of about 2,500 pounds, but then on the one field we actually did see a decrease of about 20,000 pounds. But if we look at that from a net standpoint, we're adding 80,000 pounds a year across the watershed if we implemented this practice on every possible acre with respect to phosphorus. Again, as I said, the studies, again, this is four studies, 10 site years of data, and none of those studies reported surface effects, which we were able to show, and that's where we're getting the largest impact with respect to adding phosphorus back into this system. So what's the potential here? If we look at the binational agreement and the phosphorus target reductions, the 40% reduction from 2008 loads, the 2008 water year loads were 835 metric tons. If we reduce that by 40%, that's 501 metric tons. So that gets us about 2.4 million pounds of dissolved phosphorus that we're trying to meet. Okay? So the potential impact of this study, we're not going to see anything from the surface and tile. In fact, we're going to add phosphorus, is what our data, preliminary data shows. If we even look at the previous studies, though, of this average of 56%, the reduction would only equate to about 9% of this target. And that's if we applied it in every field that was possible. And again, keep in mind those studies did not measure the surface effects. So in summary, drainage water management, it's a water quality practice. It's not an agronomic practice. Previous studies show that drainage water management will decrease tile drainage, nitrate, and DRP loads. In this study, we showed that it will decrease tile drainage discharge. It will decrease the nitrogen loading from tile drainage. But the effects on dissolved phosphorus are both mixed and minimal at best. So conclusions, drainage water management will not, or will reduce the discharge in nitrate from tile drainage, okay? Understanding the resource concern and the associated trade-offs with drainage water management is critical before we implement this practice. We have to understand what that resource concern is. In the Western Basin, it's primarily phosphorus. We need to understand that there's a trade-off okay? And that's not to neglect nitrogen. Nitrogen is absolutely very important in the Western Basin as well. So when we're talking about implementing this across the watershed and can benefit 9 million pounds of nitrate nitrogen, that's beneficial. But it will not address the dissolved phosphorus issue in the Western Basin. Again, this data came from 2 fields, okay? 2 fields out of how many in the Western Basin? We need to understand that more research is needed, and it takes time. But again, that's something I think that we need more of in order to understand what the impacts are across other soils, other management types of systems. So with that, I just need to thank the funding partners associated with the Edge of Field network, and there's over the years there's been a lot of those. The team that makes it happen. I said I get the joy of standing up here and talking. They do the work. So they obviously do the heavy lift here. With that, I'll answer questions. No questions. Everybody's ready to go home. So we normally don't put them on. So the structures are generally designed for 2% or less. You can put them on. There are water gates where we can actually benefit. If the tile drains are designed properly, you can actually stack them up a slope to where you can put them on sloping ground.